Hope you all are doing well. Today we'll be covering Encoders and Decoders 1.0. Good to have you all with us. So kicking off, we start off with what are encoders and decoders. Encoders are basically logic circuits which change a set of signals into a code using a certain logic. It has a set of input signals of which only one line is active at a certain instant of time. Decoders, on the other hand, are logic circuits which accept a set of inputs that represent a binary number and activate only the input that corresponds to the input number. It produces only one output as high for an input set. That was a basic definition for what an encoder and decoder basically is. Nowadays, data is encrypted using a 128-bit encryption, which means it has 2 to the power of 128 possible combinations. Do the math, it's a huge number which generally a hacker would find tough to crack. This is widely regarded as immune to brute force attacks from hackers simply because it would take too long to crack. Encoding is the process of transforming data, or data if you want it, into a different format using a method that is publicly available. The purpose of this transformation is to increase the usability of data, especially in different systems. Because you might have a working system, but the receiving party doesn't have the same thing. So a uniformity always helps. It is also used for reducing the storage space required to store data and for transferring the data across different channels. Decoding is the reverse process of encoding, which converts encoded information back to its original format. Encoded data can be easily decoded using standard methods. For example, decoding binary coded decimal, which is BCD, requires some simple calculation in base 2 arithmetic. Decoding ASCII values is a straightforward process since there is a one-to-one mapping between characters and numbers. The term decoding is also used for digital to analog conversions. In the field of communications, decoding is the process of converting received messages into a message written using a specific language. This process is not as straightforward as the previously mentioned decoding schemes, since the message could be tampered due to noise, etc. in the channel which is used for communications. Decoding methods such as ideal observer decoding, maximum likelihood decoding, minimum distance decoding, etc. are used for decoding messages sent via noisy channels. What is the difference between encoding and decoding? Encoding and decoding, as we've made very clear till now, are very different and opposite processes. Encoding is done with the intention of increasing the usability of data in different systems and to reduce the space required for storage, while decoding, on the other hand, converts encoded information back to its original format. Encoding is done using publicly available methods and can be easily reversed, which is decoded. For example, ASCII encoding is just a mapping between characters and numbers, so decoding is quite straightforward. But decoding messages sent via a noisy channel will not be as straightforward or easy because the message could be and most probably will be tampered with noise. In such instances, decoding involves complex methods that are used to filter out the effect of noise in the message. Now that we have understood the basic concept of encoding and decoding, let's move on to the applications. We'll start off with the application of encoders. We have keyboard encoders, positional encoders, and we have a more common application, which is the magnetic positional control, which is used in ships for navigation. Moving on to the applications of decoders. In digital electronics, a binary decoder is a combinational logic circuit that converts a binary integer value to an associated pattern of output bits. They are used in a wide variety of applications, including data demultiplexing, 7-segment displays, and memory addressing decoding. The largest impact of encoders and decoders on human lives has been in the field of communication. Coming to the field of communication, we have the mobile phones. Any communication device has the usage of encoders and decoders in it. Did you know that mobile phones and mobile network towers both use encoders and decoders? Now just imagine for a minute if these encoders and decoders didn't exist or even didn't work for a day.
Hello, this is the logic gates for an encoder. It's a 8 to 3 priority encoder, so I'll try to prove this truth table. First, I need to show you guys that this is X, and this is Y, and this is Z. Okay, and then this is D0 until D7. Okay, we'll gonna choose a random input here. Say we'll take this one. Okay, so it's D5, that is 1, so this is D7, D6, and this is D5, and all other is 0. Okay, let me just do that. Okay, for encoder, it uses an OR gate, meaning that if one of it is true, then it will have a true value. So let's see here, beside this one, it won't have a true value. So this is 0, 0, and 1, and 0. So you'll get 1. For this one, you have 0. This one also you will get 0, you will get 0, and then you will get 0. So this is 0. Okay, and then the last gate, or the X gate, this is 0, you get 1, and 0, and 0. So you'll get 1, 0, 1. So here, guys, you can see that we get this answer here. So this is true, I mean it's a true logic gate. Right here we have the logic gates for a decoder, a 3 to 8 line decoder. So I'm going to try to prove it here. This is Z, Y, and X inputs, and this we have D0, D1, D2 until D7. So I'm going to take a random value here, and I'm going to choose this one. Be careful not to screw up the order. 0, 1, 1. So okay, this is a NOT gate, so that means it will change it to 0 and 1. Over here also it's 0 and 1. This is 1, and this is 0. We'll see the this is AND gate, meaning that both or all should be true, so that the value will be true. Or if one is true and then the other is false, then the value will be also false. So here the first line is 0, and the second line is also 0, and the third line is 1. But this is an AND gate, so it will get 0 here. Here we'll get 1, we'll get 0, and we'll get 1. Still we are going to get 0 here. This is 0. The second one is 1, and the third one is 1. We'll get 0 also. Over here we have 1, and the second one is 1 also, and the third one is 1. So we'll get 1. Okay, the first one here will get 0, second one will get also 0, and the third one will get 0. So this is 0. Here we'll get 1, the second one will get 0, the third one will also get 0. So we'll get 0 here. First one here, we're getting it 0 value, false. The second one is 1, and the third one is 0. Get 0 here. Okay, the first one here is 1, second one is 1, the third one is 0. Actually, because this is a 3 to 8 line decoder, you should only get one true. So here we get D3 is equal to true, and let's find out. It's the answer here. Oh, okay, yeah, it's correct. So that's it, guys. Thank you very much. Hi, today I will show you a little bit of a walkthrough and a little bit of explanation on Verilogs for encoder and decoder. Well, first off, we'll start with encoder. I have the codes here with me. At the top of it, just like any other Verilog codes, we needed to start it with module and then give it a name for your program. So here I named it encoder, and also use encoder in and encoder out for the output. Here I have input 7:0 and output 2:0. This means I have 8 bits. Also this I have 3 bits. So here I use reg for the encoder out. Here I will use case. Using case, meaning that it will go through this list, following its order to check whether the binary inputs, and if it's true, and then it will give out the outputs, binary outputs. So here we use hexadecimal. We have 8 bits here, and we use hexadecimal value of 1, which is equal to let me check it. Have the codes here. Hexadecimal value of 1. The binary value is 00000001. We have 8 bits here. Little problem minimizing it. So the inputs, we have 8 inputs, and we have 3 bits, 3-bit output. We end case, and that's it. So next we see the decoder. Just like before it, we started with module, again give it a name and named it a decoder. We have decoder in and decoder out for the output. Here we have input of 3 bits. The output is 8 bits. Here also I use reg, and for decoder I use assign variable, meaning that it will test it individually. Here we have 3-bit binary input, which the value is 000, and if it's true, we have 8 bits binary output of 00000001, just like we tested before. So we test it again using binary input, hexadecimal output of 4. Let's test it. 4. So here we have the binary value of 00000100. It will be the same here. 10. Okay, next step, we will try to simulate it. Alright, so we will try to simulate the Verilog codes of the encoder and decoder that we've just discussed before. So over here we will I will use Altera Model Sim to simulate the Verilog codes. So I will use the jumpstart button and then create a new project. Rename project name and a simple name of encoder. We create a new file, just call it simply as encoder, and change the file type as Verilog, because this is Verilog code, so we will use the file type Verilog. Click OK. Double click the file and copy the codes that we have before. Copy, paste it. So after that, we need to save it first. Click the button and then compile it. Right click and compile selected. Here we have a successful compilation, and the next step is to simulate the project. We start the simulation and search for our project, the encoder, and press OK. OK. Here you will see it changes into simulation mode, and we have a wave. So here I will put encoder in and encoder out. The next step is to test the logic gates that we've coded into the module. So I'm going to force the values of encoder. We have 8 bits, so we will start with 0 0 0 0 0 0 0 1. It's 8 bits here. Let me see, 1 2 3 4 5 6 7 8. Okay, and then we run the simulation by clicking here. Here you will see that the output we get is 0 0 0. So what if I change the value to be like this? So I run it again and we get another value. The encoder is 1 0 0. And then if I change it again into 1 0 0 0 0 0 0 0 and run it again, we will get the output is 1 1 1. So let me check it with a truth table that we have. So for 0 0 0 0 0 0 0 1 we get 0 0 0, and for 1 0 0 0 0 0 0 0 we get 1 1 1. So it's validated, and that's it. The next step is we will create a new module, a decoder module. Let me add to project as new file, call it as decoder. Again, we pick Verilog. Double click it and copy the codes that we have. Paste it. Again, saving it and then compiling it by right clicking, compile selected. Here also we have a very successful compilation of the codes. So after that, we will try to simulate this decoder by clicking simulate and start simulation. Go towards the project that we have and decoder. Here we have the objects of decoder in and decoder out. It's different with the encoder before, because before is encoder in and encoder out. So we check the wave and drag it down here and force the value to be 3 bits input. So we will start with 0, 0, 0, and then we will test it. So here we get 0, 0, 0, 0, 0, 0, 1. So this is exactly the opposite of an encoder, because it changes back from 3 inputs, 3 bits into 8 bits. So test it with one more or 2 more. Run it again and we will get different value and a customary 111. Test it. Yep. And let me, okay, so the same like before, we have we have validated the input and output. We have 111 and then starting with 1, 0, 0, 0, 0, 0, 0, 0. So that's all for the simulation and validation part. Thank you.